Welcome to the Explainer. Today, we're tearing down the absolute foundation of modern multimodal AI, the vision transformer and the patch token primitive. Whether you're looking under the hood of a 2026 frontier model like Claude Opus 4.7, Gemini 3.1 Pro, or Qwen 3.5 Omni, you are going to find this exact mechanical pipeline right at the very beginning of the process. So how do we actually get a language model to see?
Well, to answer that, let's look at this absolutely impossible under, 150,528. That represents the exact amount of tokens a tiny 224 by 224 pixel image would create if we tried flattening every single pixel for a transformer to process. Remember, transformers eat sequences. Text is already a sequence of words, but image, that's a 2D grid with 3 color channels. If you try to feed over 150,000 tokens into standard self-attention, which, scales quadratically, the computing power required instantly becomes a total non-starter.
So to figure out how we beat that massive sequence length bottleneck, here's our agenda for today. The image sequence problem, patches as visual tokens, positioning and pooling patches, pre-training vision models, and finally, we'll look at the 2026 production standard. Let's get right into it.
Part 1. The image sequence problem and why convolutions used to rule. We really have to start with that fundamental friction we just mentioned. Transformers just fundamentally cannot eat 2D grids directly.
For years, the industry's band-aid for this was basically bolting a convolutional neural network, like a ResNet, onto the front of a transformer. The CNN would extract a feature map, and those features became the tokens. But doing that inherited all of the CNN's biases, and it totally bottlenecked the transformer's massive appetite for scale. That was just the status quo. That is, until the original 2020 Vision Transformer paper dropped this absolute bombshell of a heretical question. What if we just skip the CNN entirely?
Which brings us to Part 2. Patches as visual tokens. This is the core primitive, and it's the exact mechanical solution we still rely on today to solve that historical sequence problem.
Here is your fundamental vocabulary for the rest of this explainer. A patch. Instead of force-feeding individual pixels, we carve the visual grid up into fixed, non-overlapping cubes. Think of a 16 by 16 pixel square. That single square is a patch, and it's going to become one single token.
Let's peek under the hood at the actual pipeline. Take a standard 224 resolution image. First, we carve it into a 14 by 14 grid, giving us 196 patches. Next, we take one of those 16 by 16 patches, which, remember, has 3 color channels, so it's really a cube of 768 pixel values, and we flatten it. Then, we apply a shared linear projection to map it to our model's hidden dimension. And finally, we add a positional embedding. This is absolutely crucial, because without it, the transformer has literally no clue if a patch is the sky at the top left or the grass at the bottom right.
Now, for the engineers tuning in, here is the really cool part. This elegant mathematical linear projection, in production code like PyTorch, it is practically executed using a super simple, highly optimized 2D convolution. It's just a con2D with a kernel size and stride equal to your patch size. It is incredibly efficient.
Moving to Part 3, positioning and pooling patches. How do we organize the bag of tokens? Because without structure, the transformer is just staring at a disorganized pile of visual patches.
We have to distill all these independent patches down into a single image-level summary. We have 2 main ways to do this. First, the classic CLS token inherited from older models like BERT. You basically just stick an extra, learnable token at the beginning of your sequence, and whatever its state is at the very end becomes your summary. It's fine for simple classification. But the newer approach is mean pooling. You literally just average out the output states of all your patch tokens, and that is the standard for modern vision language models today, like SigLIP and Dino V2.
But here is a wild wrinkle from 2023. When you train these models at massive scale, researchers noticed vision transformers develop these weird, high-norm artifact patches that totally hijack the self-attention mechanism. To fix it, they introduced register tokens. Think of them as digital sponges. They're scaffolding tokens added specifically to soak up those distracting artifacts, which dramatically improves dense tasks like segmentation. And the best part? Before handing the sequence off to a language model, these register tokens simply get discarded. They clean up the mess, and then they're gone.
Part 4. Pre-training vision models. Let's look at how this primitive evolved. We have the mechanics down, but how do we actually teach this architecture to understand what it's seeing?
This timeline is a perfect map of the relentless pace of innovation here. We started in 2020 with the original Vision Transformer, using simple supervised classification on the JFT300M dataset. Fast forward to 2021, and we shifted to self-supervised and contrastive methods like CLIP and MAE. 2023 brought us Dino V2, using self-distillation with absolutely zero labels or captions. And by 2025, we arrive at SigLIP 2, using a brilliant contrastive objective with a sigmoid loss.
The big takeaway here? Your choice of pre-training completely dictates what your vision backbone is actually going to be good at downstream. MAE is great if you just want a starting block to fine-tune later. Dino V2? That is the absolute strongest purely visual backbone right now for dense visual features. But if you're building an open vision language model, like a Lava or a Quen, you are almost certainly using SigLIP because its contrast to pre-training makes it completely incredible at semantic matching with text.
Which brings us to our final section, the 2026 production standard. Let's break down the anatomy of SigLIP 2, the undisputed foundation powering today's frontier open models. Let's tear down the exact specs of this workhorse encoder. Notice how literally every single bullet point here connects directly back to the research we just decoded. It's got 400 million parameters. It uses a slightly finer patch size of 14 at a resolution of 384, giving us 729 tokens per image. It uses mean pooling. It employs exactly 4 of those register tokens to absorb artifacts. And instead of old 1D position tables, it uses 2D rope paired with NavFlex, which allows the model to natively process multiple aspect ratios without needing a total retraining.
So, I want to leave you with this massive challenge to wrap up the explainer. Calculate the exact token cost for a high-definition video using these rules. Think about it. If a single frame at patch 14 produces thousands of tokens, what happens when you feed a language model a 5-minute video at 30 frames per second? Suddenly, you are dealing with millions of visual tokens. How do you manage that context without your LLM totally exploding? Will you pool them, sample frames, merge tokens? Figuring out that token arithmetic is the absolute frontier of multimodal AI today. Thanks for joining me on this deep dive.